Okay, okay. Hello, everybody, to this week's ISGC seminar talk. This week's speaker is Vicharit Yingcharoenrat. He got his PhD from CISA in 2021. Then he did a postdoc at the Kafli IPMU in Tokyo. And now, since 2024, he is a faculty member at the Department of Physics at Chulalongkorn University. And we will talk to us today about non-perturbative wave function of the universe in inflation with resonant features. Thank you very much, Vicharit, for agreeing to give this talk. The stage is yours.
So thanks a lot for the introduction, Robin, and thanks a lot for the inviting me to give the talk in this wonderful online seminars. And so the topic I'm going to discuss today is the non-perturbative wave function of the universe in inflation with resonant features. And this work is based on these two papers, and also it's based on some work in progress. I've been collaborating with Paolo Climinari, Sebastian Neubetel, and Giovanni Tambano. So yeah, so if you have any question, please interrupt me anytime. Okay. So here is the outline of my talk. So first, I'm going to give you a little bit of the introduction, motivation, why one needs to go beyond perturbation theory in inflation. Then I'm going to show you the EFT, or effective field theory of inflation in the decoupling limit. I will tell you why we are interested in this type of the theory. And then I'm going to show you how to compute non-perturbative wave function for the resonant models. So you will see that this wave function will be oscillating as a function of the amplitude. Okay. And then the conclusions. Okay. So let me start from the basics, which is pseudo inflation. I'm sure for this audience, you guys are more or less familiar with this inflation. So basically, inflation is just the phase of in the early universe, which the universe expanding exponentially. So you have a double dot being positive. A is the scale factor. Okay, and usually one assumes pseudo conditions, and so you have like a single field, and then this single field slowly rolls down the potential. And then, so in this approximation, basically the metric is approximately the zeta space. So basically this scale factor is like e to the Hubble times t. Okay, so h here is a Hubble parameter, which is more or less a constant in this approximation. Okay, so and the important parameter in this regime is the pseudo parameter, which is epsilon, which controls or quantifies how far you are in the zeta limit. And so in this approximation, one can write down the metric in this way. So this eta is a conformal term, okay, and it runs from minus infinity to 0. Okay, and here we are writing this metric in the flat slicing thing. Okay, and so this is a story of the background evolution. So you have exponential of the scale factor and so on, okay, in the pseudo regime. So you can go to a fluctuation level so that in which you can compute the so-called curvature perturbation. And so you introduce this curvature perturbation in front of in spatial metric Hij. So you have this zeta, and zeta is a scalar fluctuation here. And you can, for example, compute this two-point function of zeta in k space, and it goes like 1 over k cube, and with some amplitude p zeta here. Okay. So so this 1 over k cube is a features in this model because it's a fact that you have scale invariant symmetry in this the zeta limit, and this amplitude p zeta can be fixed using the CMB data. So on the last scale, like on the CMB scale, this p zeta can be fixed to be around 10 to the minus 10. Okay, so this number, and then zeta is around 10 to the minus 5 more or less. Okay, so so what I wanted to say is that whenever I refer to typical fluctuation, I refer to the CMB value in which zeta is around 10 to the minus 5. Okay, so when I do non-typical or far from the peak of the distribution function, I compare with this number, okay, 10 to the minus 5. Yeah. Anyway, so this is the story of the two-point function and so on, okay, which is very standard. And then you can go beyond a 2-point function to consider, like, for example, 3-point function, 4-point function, and so on. Okay, so around the typical fluctuation, one can compute this 3-point function, 4-point function using the in formalism or using perturbation theory. So you see that from this map, you have a 2-point function, and then here you have a 3-point function, and here you have a 4-point function, and so on. Okay. And so let me just try to estimate how large is 3-point function, for example. So from Planck data, we have upper bound for the FNL equilateral. Equilateral means these triangles, they are the same size. So this FNL equilateral is less than around 100. So if you want to know the correction to the Gaussian, and what you have to do is you have to take this 3-point function and divide it by this p theta 3/2. And essentially, this is just FNL times square root p zeta. And p zeta, you know that is 10 to the minus 10, no? And then this FNL is 100. So this essentially is around 10 to the minus 3. Okay. So this number is telling you that as long as this FNL times square root p zeta is smaller than unity, that means you are in the regime of perturbation theory. Okay. So here is a constraint from Planck, which is FNL equilateral and FNL orthogonal. Okay. So also in the Sororo inflation, where you have just the potential, you can compute also the local type of FNL, which is proportional to Sororo parameter eta or epsilon. Okay, and it's very small. Okay. So what I wanted to stress in this slide is that the only expansion parameter in perturbation theory is FNL times square root p zeta. Okay, nothing else. And this turns out to be your coupling constant in your model. So suppose you take any of your favorite model inflation, and then you expand up to cubic order, and then you have some coupling in front, and it turns out that this FNL times square root p zeta is your coupling constant. Okay, and as long as this coupling constant is less than unity, then you can use the perturbation theory as usual, like using in formalism to compute 3-point function, 4-point function, and so on. Okay, nothing strange. Okay, right. And so this is story of the perturbation theory. Okay, and what about wave function? So suppose I give you this PDF of zeta, and this PDF or the probability distribution function can be computed from the square of the wave function. Okay, just in a quantum mechanical sense. Okay, this wave function square. Okay. And one can define this wave function in this way. Okay, using the path integral. So essentially, this wave function is a function of the delay time amplitude. Zeta bar is the amplitude of the fluctuation living on the late time boundary. Okay, so remember that the eta here runs from minus infinity to 0, or eta f, and this zeta bar is the object that lives on the late time boundary. Okay, and now this wave function can be computed using this path integral, and then you start from the vacuum omega here, and then you evolve zeta, or your field, up to this zeta bar, and this zeta bar is on the boundary, on the late time boundary. Okay, right. And then, as usual, you can compute the correlation function zeta of zeta, endpoint function of zeta, using this formula. So you can just multiply this zeta n with the wave function squared, and then you can get this endpoint function of zeta. Okay, so far this is just a standard computation of endpoint function. Okay. Okay, so let me go. So okay, so now how do we go beyond perturbation theory? So sorry, let me go back to this perturbation theory. So in perturbation theory, what you do is you expand your wave function. No? You expand. Let me go back. So you essentially you expand this exponent, the action, order by order, like starting from Gaussian, and then you have correction to the Gaussian, which is 3-point function and 4-point function, and so on. Okay, this is an expansion in perturbation theory. Yes. So this part is Gaussian, and this part is non-Gaussian. So it's just these are just the correction to the Gaussianity. Okay, and you can relate the two-point function to this coefficient of the wave function psi 2. And yeah, so for example, this real part of the wave function coefficients give you the two-point function of zeta. Okay. Why real part? Because you remember that when we compute when we compute this two endpoint function, we have to square the wave function, and then this square means you pick up the real part of the wave function coefficients. Okay. So you pick up the real part of this guy. Okay. And the imaginary part of this guy does not contribute to any physical observables. Okay. And also for the three-point function, is proportional to the real part of this psi 3, okay, which is a three-point wave function coefficient. Okay. And actually, one can compute this psi 2, psi 3, psi 4, and so on using the so-called Witten diagram. And then this is like a Feynman diagram, but you have late time boundaries. Like for example, here, if you have the interaction like this, zeta prime to the fourth, prime is a time derivative. And then you can compute this psi 4 at 3 level. And here in this diagram, you need 4 bound to boundary propagators. Okay, 1, 2, 3, 4, and then you have one vertex, okay, lambda. And here is correction to the two-point function here, correction to the psi 2 here, okay, due to the loop diagram. Okay. Okay, so here, yeah, like for example, in this diagram, you need to have bound to boundary, and also you need to have a bound to bound propagator like this. Okay. Right. So far this is a study in the perturbation theory, and now so suppose we want to go beyond this perturbative regime. So what you have to do is, okay, so let me start from this PDF of zeta, and you have this Gaussian part plus some correction here, 3-point, 4-point function, and so on. Okay, and so I remind you that this expression works only when you are around the peak of the distribution function. Okay, so you're not really far away from the peak. And so if you factorize this Gaussian piece out of all the terms, you see that now the expansion parameter becomes f and l times the psi of the field times the psi of the zeta here. So before it was p zeta to the 1/2, right? And now it becomes this theta, and this theta is essentially, it means the comparison between your zeta and the typical zeta, okay, the one of the CMB 10 to the minus 5. And also for the 4-point function, you have g and l times zeta squared. Okay. So now what it means here is that the fact that this expansion parameter depends on the size of the field. Okay, it means that as you go to the tail of the distribution function, you go away from the peak. That means your perturbative expansion breaks down. Okay, so here in this plot, the blue line is the Gaussian one. Okay, the blue line is the Gaussian one, and the red one is non-Gaussian. Okay, so you see that around the peak of this PDF, you can use this expression, and then perturbation theory works fine. Okay, but as you go to the tail of this distribution function, and when the psi of theta is of order 1 over f and l, that means your perturbation theory breaks down, and whatever you want to capture here on the tail of the PDF has to be in a non-perturbative way. Okay, so yeah, so here in this talk, we wanted in this project, we wanted to see how the statistic of the tail behaves in this large field limit. Okay, so essentially in our previous paper, we take this single interaction of theta, like derivative interaction, lambda theta prime to the fourth, and then so we found that this red one, the tail goes like e to the minus theta bar to the 3/2. Okay, theta bar is I remind you, is a late time amplitude of our field of our theta. Okay, and you see that this is this power 3/2 means that you are away from the Gaussian tail, and this cannot be captured by any order in perturbation theory. Okay, so yeah, so the blue one goes like Gaussian, e to the minus theta bar squared, but no, here is the fraction, so it's 3/2. Okay, anyway, so I remind you that as you go the large field limit or to the tail. That means perturbation theory breaks down, and then you have to do everything in the non-perturbative way. Okay. I will tell you next slide why we are interested in this regime. So, but in this talk, we are focusing on this kind of behavior of the tail. So essentially, this we are interested in these oscillating features of the wave function. Okay, so you see that as you go to the tail, as you increase the value of zeta, this wave function here on the PDF starting to oscillate around Gaussian. Okay, and so you see that you can imagine that how to say, like you have a cosine potential, and then if you truncate, you can expand the cosine, right? Around this peak, you can expand the cosine, and then if you do calculation in perturbation theory, you have to truncate at some order. But if you truncate at some order, then you cannot recover this oscillating function. So you have to, essentially, you have to resum the whole cosines. Okay, you cannot truncate at some finite order. So essentially, these non-perturbative features amounts to resumming the whole series, the whole expansion series. Okay. Anyway, so yes, now you have this. You need to resum this the full perturbative series to recover the full features, non-perturbative features. Okay. All right. So yeah, so now we are focusing on this kind of behavior. Anyway, so a little bit of the motivation why we are interested in this the tail of the distribution function. So you know that now we have research that really like PBH, which is the primordial black holes that typically happens around when the mode function re-enters the horizon, and then if the amplitude of that guy is larger than the threshold, then you can form the PBH. And so, like for example, here the mass fraction of PBH, you have to integrate from the threshold of the theta and then up to infinity, and you have to integrate this kind of PDF. So you see that it's very important for us to to properly determine the statistic of the tail of this PDF. So it's very crucial for people to determine the PBH abundance in this case. Yeah, but it's just the motivation for us to But anyway, so in this talk we are not going to connect to PBH. We just give you some example of our non-perturbative wave function, and then we leave this PBH connection to future work. Okay. Anyway, right. Anyway, so the way we do the computation because now we are on the tail of this PDF. So the way we do the computation is to use the so-called semi-classical limit. So because the event we are going to consider is really unlikely or it's very rare. That means you are essentially, because we are going to compute this wave function, which is e to the is divided by h bar. S is action. And then as you go to the tail, you can imagine that the value of the field is becoming larger and larger. And then that means the action also becoming larger and larger compared to h bar. So the more you are in the tail, the more you are in the semi-classical limit in this sense. Okay. But the fact that we are using semi-classical limit doesn't mean that we are computing classical object. We are still computing wave function, which is a quantum mechanical object. Okay, it's like you use WKB approximation in quantum mechanics in this sense. So we are going to use the semi-classical approximation to compute our wave function. Okay, and as you know, in order to use the semi-classical approximation or semi-classical limit, you have to find the classical trajectory that dominates others, and then you have to plug that back to the action, and then try to evaluate the action, the onshore action, and then you at the end you have the wave function. Okay. I mean, then our task is to find the classical solution. Okay. But okay, so let me just give you the recipe how to compute a non-perturbative wave function. Okay, so we are going to compute this wave function defined in this way, and then in a semi-classical approximation, you can approximate this path integral as e to the is evaluated on the classical trajectory. Okay, and then here we neglect the prefactor, which is high order in H bar. Okay. Anyway, so the first thing you have to make sure is that you have to have the fully nonlinear action in zeta. Why? The reason is that the fact that you need to have fully nonlinear action in zeta, because you can imagine that as you go to the large zeta limit, large field limit, you might going out of the regime of the EFT, because high order operators might becomes important in your EFT, like for example, zeta to the 10, zeta to the 100, and so on. This operator can become important as you go to the tail and your EFT breaks down. Okay? So we have to make sure that as you go to the tail of the distribution function, the action you are considering is still valid. Okay. So that's the first thing you have to make sure. Okay. And the second thing is that after you have this fully nonlinear action in zeta, you write down equation of motion in Euclidean space. Okay. Why Euclidean? Because okay, you know that in Lorentzian things is because you have this e to the I k eta, like the mode function. So in Lorentzian, so that means when you go to early times, when k eta goes to minus infinity, that means your mode function oscillate like crazy. So that you don't have a control in Lorentzian. But okay, in Lorentzian, one can use the I epsilon prescription to shut off this oscillation, but one can also fully rotate to Euclidean and do the calculation in Euclidean. Okay, and in Euclidean you have the nice exponential decay at the early times. Okay, and then at late times you impose some boundary condition here, set a bar living on this boundary, and then you just now you have to look for the nonlinear classical solution. Okay, and then at the end you evaluate your action on this nonlinear classical solution. Okay, and well, this leave for the future work. As I said, we have not yet done this kind of connection to PBH yet, so we leave this thing to future work. Okay. Because you know, in order to compute the PBH abundance using our method, one has to vary overall the late time profiles. Okay, that living on the late time boundaries. So in our case, we just fix the late time boundary to be just specific profiles, and then we ask what is the probability, or what is the wave function. But in order to connect to the PBH, you have to vary over all the late time configurations, and then require this condition, the condition that the amplitude is larger than the threshold of the formation. So yeah, that require another, how to say, another functional integral. So that we leave to future work. Okay, so we stop here, and then so essentially we just find the wave function that of or the probability of to find these late time profiles, zeta bar and late time specific profiles. Okay. Anyway, so let me go to, yeah, so just a simple example in free theory. Okay, I think most of you familiar with this kind of action. So this is just the action for scalar perturbation in the system. So you have this kinetic term, which is time kinetic term, and the spatial kinetic term. And for this free theory, you can find the analytic solution for the free solution, which is written in this Fourier space. And so you have 1 minus ik eta e to the ik eta. Okay. So yeah, this is the mode function I told you before, that when you go to early times, when eta goes to minus infinity, this mode function oscillate like crazy. Okay, and well, I told you that what you have to use the I epsilon prescription to in order to shut off these oscillations at early times. Okay, and once you plug back this solution, this free solution to the action here, okay, you get the following. You get this kind of thing. Okay, so for the free action, one can use integration by part one time. Okay, and then it becomes that the boundary terms in eta in time, and then this becomes just here. That's why this free action It's just this action evaluated on the late terms, okay, on eta f. And then you expand for the small eta f because eta f goes to 0 at late terms. And then you have these pieces, okay? So yeah, so you have imaginary part here, k square divided by eta f. But this imaginary part is a divergent term. Divergent as eta f goes to 0. Okay, there's a polar here. But there's no problem because this imaginary part does not correspond to any physical observables. Okay, so we don't care about this. But the real part here contains k cube, which is essentially our 2-point function that I told you in the first 2 slides. Okay, but the thing is that in this case the wave function is just Gaussian. Okay, because it's Gaussian in zeta bar. Okay, like this, nothing fancy. Okay. Okay, so now let me just go to the form of the action for zeta, because we need to make sure that as you go to the tail of the distribution function, the action you are using should be valid there, okay, whatever it is. So we start from the if-still inflation, which, okay, I will explain later. And so first we are interested in this so-called decoupling limit. So the decoupling limit means that we are neglecting the mixing between scalar fluctuation and the metric fluctuation, okay? And essentially you take epsilon, which is a Sororo parameter, to 0, and then you fix this power spectrum. And okay, in other words, decoupling limit means that you take just exact the zeta limit. Okay, you take the background metric to be the zeta and no metric perturbations. Essentially, what it means is that you don't have to solve for the constraint. Like you don't have to solve for the shift function on the left. The shift vector on the left function. Okay. Essentially, if you take into account those mixings, the mixing with gravity, those mixing are proportional to the epsilon, to the Sororo parameter. Okay. Anyway, so here we don't care about the mixing with gravity. We just take scalar fluctuation and we go on. So we start from this EFT inflation. And for some of you who may not familiar with this form of the action, you can think of this as just the action for the of the canonical single field inflation. Okay, it's just the kinetic term minus the potential, but written in this strange way, like G00 upwards, whatever. Anyway, so you start from this, and then you use the so-called Stuckelberg trick to recover the 4D diffeomorphism, because when you write down the action in this form, the action only invariant under the 3D diffeo. But in order to recover the 4D diffeomorphism, you have to use the so-called Stuckelberg trick, and that Stuckelberg procedure introduces the scalar fluctuation here, pi, or the Goldstone boson, if you want. Yeah. Anyway, so we reintroduce this pi field in our action, and then we neglect the second order in Sororo parameters, and then what we get is this action. Okay. So now we have this action, which, so you see that this action contains this function h dot of t plus pi. Okay. So whatever here, this function h dot contains a fully nonlinear function of pi. Like, for example, you can imagine that if h dot of t is a cosine or psi function, then once you replace t with t plus pi, then pi appears inside the cosine, and then you have a fully nonlinear action for pi. Okay. Anyway, but also this action has you see that the constant pi solution is a solution to this case. If you write out EOM, equation of motion of pi, and then you see that the constant pi is a solution here. Anyway, so what I want to say is that once you take this form of the action, it contains all the nonlinearities of pi, all the features that you have in the background in h dot. Okay, so so this means that after you fix the background, fixing the background means you fix the Hubble parameter, fix the function h dot of t, and then after you fix this function, you can replace t with t plus pi, and then you get the fully nonlinear action of pi. Okay, like this. Okay, and now we are going to use this action to compute our action for pi. Okay. So, and then furthermore, you can connect pi fluctuation or scalar fluctuation with zeta, which is the curvature perturbation. So let me tell you that the curvature perturbation and the scalar perturbation pi, essentially they are not the same, but they are the same when you neglect the mixing with gravity and so on. You neglect high order terms and so on. Okay, so you can use this linear relation between pi and zeta. But it might be that after you go outside horizon, there might be some nonlinear evolution that change this relation between zeta and pi and so on. Maybe you have to take into account the nonlinear contribution of zeta and pi. But anyway, so here we are taking a linear relation between zeta, curvature perturbation, and the scalar fluctuation pi. Okay. Anyway, so let me go on. So in our model, we are interested in this kind of features of the Hubble. So first you have this constant, almost constant, h dot, because h dot is like a epsilon, no? So we take this to be a constant. And then on top of this constant, you have some oscillation or wiggles, okay, around this h dot. So you have this amplitude b theta, and then you have this frequency omega. Okay, you have two parameters here. And so now in our case, we are taking a small amplitude limit. So we are taking b theta to be very small. And we take the frequency of the cosine to be very large. So we see that. Okay. So actually, this kind of behavior of the Hubble parameters can be realized in the so-called axion monodromy inflation. Okay. And so in this case, you can take Sorolo inflation plus axion-like potential like this cosine. And so in this case, you can define this parameter alpha, which is the frequency of your cosine, divided by the Hubble. Okay. And in our case, what happened is that you have your inflaton field, which is rolling down these Wiggles potentials. Okay, so you have two parameters here, the amplitude of the Wiggles, which we take to be very small, and also we take the frequency of this Wiggle to be very large. Okay, so there's some advantage of taking these two limits. Okay. Well, the thing is that if you take the amplitude of the cosine to be very large, then it might be that your inflaton field might get stuck in some of the minimum, and then inflation stop there, and then maybe you have to consider like a vacuum decay, whatever. Okay, but now we want to have the inflation to go on, and then you have to have a small enough amplitude of this oscillation, and also we take this large alpha limiter because there will be some simplification due to this large frequency limit. Okay. Anyway, so then we take this model and then we compute our action of pi. Yeah. But before going further to the wave function, let me say some word about the resonance. So why it's called resonance models? Because of the following. So you have to kind of two oscillations happening in this system. One is the background, which is coming from the Hubble parameter. So Hubble parameter, oscillates like this because of the cosine. And then you have also the mode function, which is zeta, which is oscillating like e to the ik eta. So now you have two oscillations thing, okay? And you can imagine that once these two, coincide, there's going to be some resonance happening, right? So essentially now you have this mode function e to the ik eta, which is like this. And then you have this oscillation of the Hubbles, which is like this. And then once you multiply these two together, because essentially when you compute things like correlation functions, what you have to do is you have to multiply the mode functions with some background quantity, which is Hubble. So once you multiply these two together, what you get is this kind of thing. So you get some sort of peak happenings like this, okay? And then this peak happens at the saddle point. We call it saddle point because it's when your integration is dominated at this point. And this saddle point, you see that it happens at early time because this alpha, we take it to be very large. So early time means this eta s is very large. So you are in the deep inside the horizons. That means this kind of resonance features happen deep inside the horizons, okay? And people have been computing non-Gaussianities in perturbation theory, of course, using in informalism and so on. and they found some peculiar features in this model, like it depends on the log of the total momenta like this, and also there's some enhancement due to large frequency limit, large frequency alpha, yeah, like this. Okay, so this is just calculation in a perturbative regime. Okay, so now in our case we are in, yeah, let's go back to our fully nonlinear action for the scalar fluctuation. So here we just take this action for pi, and then we take this, yeah, the behavior of the hyperparameter, which you have a constant, and then you have some modulations around this, small modulation around this Hubble dot. And then you plug this back into the action, and then you see that now you have a fully nonlinear action for pi here. So now you see that the pi appears inside the cosine, and this is fully nonlinear function in pi. Okay. Okay. So essentially, in this model, if you go back to your perturbation theory, what you do is you are going to expand the cosine. Okay. You expand cosine like 1 plus pi square plus pi to the 4th and so on. And then you are going to have a tower of interactions of the tower of self-interaction of pi's. And then you can compute, for example, 2-point function, 3-point function, 4-point function, and so on. Okay, after you expand the cosine. Okay. But here I emphasize that we are not going to expand the cosine. We keep pi like this. We keep the cosine as it is, and then we compute the full action. Okay. And now, yeah, you can now you can write down. Yeah, the thing is you have to solve for the nonlinear classical nonlinear solution for pi with some appropriate boundary condition, as I said, starting from the vacuum at early times, and then you end up as some late time configuration, and then at the end you have to compute the on-shelf action. Okay. But actually, the fact that we are in the small b tilde limit, the fact that we are in this small amplitude limit, means that we can use the free solution in pi. Okay. Okay. Now things become maybe a bit confusing, because we are in the perturbative regime in b tilde, but not in pi. Okay. Not in the side of the field, but in the amplitude of the oscillation. Okay. So in this limiter, you can show that at first order in b tilde, you can just use the free solution of pi and then plug it back to the action. And also, the free solution of pi has been was obtained, is like 1 minus ik eta e to the ik eta. So you know that free solution, and then you can plug that back to the action. Okay. But I told you that this is not a trivial procedure, because even though you know the free solution of zeta, but it's still a very complicated computation to do, because you have to, this zeta is a zeta in real space, in X space, and then the one is the one in K space, in the Fourier space, 1 minus ik eta e to the ik eta. Then you have to essentially Fourier transform back to the real space, and then you have to plug into the cosine here. And after you plug it here, you have to do another integration in eta. Okay, so there are many steps to do here. Let me go on. Anyway, so I think I don't have much time to discuss about the diagrams. Anyway, so if you guys are interested in understanding the diagrams, I can tell you a little bit. So essentially, the exponent that we are computing, like this on-shelf action, essentially this on-shelf action means that you are resumming the 3-level Witten diagrams here, just a 3-level. And why is a 3-level? Because you can compute this diagram one by one, and then you know that this diagram scales like alpha squared times zeta bar. Okay, so this alpha squared times zeta bar is our expansion parameter here. Okay, this is nonlinear classical expansion parameter here. It's like FNL times zeta that I showed you before. Okay, and once this parameter is become of order unity, that means you cannot use perturbation theory, and then you expect to see some non-perturbative features like oscillation and so on. Okay, and moreover, we have to be careful that once we are in this large zeta limit, we have to be careful that the quantum corrections, the loop corrections, so on, these corrections should be under control. That means that all of these diagrams should be small. compared to this three-level diagram. Otherwise, you cannot use the EFT. Anything breaks down. Okay, you break unitarity and so on. Okay, but it turns out that the quantum, how to say, the quantum expansion parameter is like alpha square times p zeta, and this alpha square times p zeta is very small, because p zeta here is 10 to the minus 10. Okay, so you make sure that as you go to the tail large zeta limit, this loop are still under control. Okay, at first order in BTU, by the way. Anyway, so let me just show you how to compute the action. Yeah, so so go back to this action, and then what we have to do is we have to plug in the free solution of zeta, and then we have to do the integration here, many integration in fact. And so let me just skip. So yeah, so essentially you can split your the action into two pieces. One is the Gaussian delta S0, and the other one is a correction. It's the oscillation part coming from the cosine. Okay. Here, okay, delta is, well, this is just a technical piece anyway. So delta means we subtract some divergence p that we know analytically. Like, remember that how to say, the free part contains the divergent piece, which is a 1 over eta f. So that's why we want to subtract that part. Anyway, so the free one, you know how to compute, which is already known. And for the this delta S1, which is a corrections to the free part, to the Gaussian part, you can compute it using the free solution of zeta. So essentially, you know this free solution of zeta in K space, and then you have to Fourier transform back to the real space here. And after you obtain this zeta of tau and x, then you plug into this cosine, and then you do another integration in tau here, and also in space. Okay. So you see that now is involved many integrations that you have to do, and it's and we do all these things numerically. Yeah. Okay. Yeah. So but essentially what we assume here is that we assume we assume that the Latam profile has a spherical symmetry. So it means that we reduce our 3+1 problem effectively into 1+1 problem. Okay, instead of having the full angular theta, phi, whatever, but we reduce those parts, and then we have just the t, tau, and r. So you have to integrate in over time and over the radius. Okay. Anyway, so I skip this thing, and then here is the result. So here we obtain the correction to the wave function, which is the delta S1, and then this delta S1 is oscillating as a function of late time amplitude theta bar. Okay, and you see that this oscillation happens when this parameter alpha square times zeta is of order unities, and that means this is you're already in the non-perturbative regime here. Yeah, and then different color means different values of alpha. Okay, and then you have this oscillating features of the wave function here. Okay, and essentially this kind of behavior you can use standard point approximation to evaluate the integral, because to evaluate the last two integrals. Okay, you can use standard point approximation to approximate these integrals. And I'm not going into the details, so I just mentioned that when you do the saddle point approximation, the saddle point in this case happens at late time. So it goes like 1 over zeta bar. Zeta bar, is a late time amplitude. So as zeta bar is very large, then this saddle point happens at the close to the late times. So before in the perturbative regime, remember that this saddle point happens inside the horizon, close to the early times. But now as you increase the size of the field, or the size of the late time amplitude, this saddle point is shifted towards late times. Okay, and then you can use this saddle point approximation to to compute this delta x1. And the thing is that here in this analytic formula, you see that this delta x is oscillating as a function of zeta bar. Okay, and moreover, you see some enhancement factor, which is e to the alpha pi over 2, and alpha is very large, so you have some enhancement factor here, and this is for the positive zeta bar. Okay, and so the saddle point approximation result is given by this the dash line, and then the orange one is coming from the numerical calculation, and these two methods matches. You know, when you go to very large zeta bar, and of course, when you go to small zeta bar, it's start to deviate from each other. And so the point also now, the more interesting point is that the zeta bar, the amplitude of the late time configuration can take also the negative value, because you can think of the PDF, you can go to positive or you can go to negative, you know, side of zeta. And if you go to negative side, what happened is that the wave function here now, or the action, is still okay. It's still oscillating in zeta bar. It's still oscillating in the amplitude of the late time configurations, but there is no enhancement factor. The factor that was before in the positive side wasn't here in the negative side. E to the alpha pi over 2 here is absent here in the negative side. Okay, so now and so now that means the wave function, our wave function now is asymmetric between this positive and the negative zeta bar. Okay, right, and right. So here is a comparison between our numerical result, this blue one, and the saddle point approximation here. Okay, and the amplitude here is very small. I think if it compared to the positive case. Okay. Anyway, so let me mention perhaps my last slide. Let me mention what we are trying to do now. Because so far I've been discussed about the tail large zeta limit, how to do the computation on the tail, how to capture statistic of this wave function on the tail and so on. But let us get back to the typical fluctuation. Let us get back to the perturbative regime, okay, where the typical value of power spectrum is 10 to the minus 10 from CNV. And so in this regime, it has been found that one can push, because usually when you take the cosine potential, you know, the typical cutoff is around 4 pi f. Okay, so 4 pi f means that when you reach the energy scale 4 pi f, that means you sort of expect that the new physics or the physics of the UV might play some role, or your EFT breaks down there. Okay, somehow, then you cannot trust your calculation and so on. Okay, and then, but it has been shown that in fact, this cutoff, this naive cutoff of the cosine potential 4 pi f can be pushed to a larger cutoff. Okay, so the new sort of unitary cutoff can be pushed to larger value. So you have some window between 4 pi, the usual 4 pi f, and the new cutoff. Okay, and this new cutoff depends on the amplitude of the oscillations. Okay, so the fact that it depends on like 1 over b tilde here, you see, no, the smaller b tilde, the larger this new cutoff. That means if you send b tilde to 0, it means that your new cutoff goes to infinity. So when lambda goes to infinity, that means your theory is completely free. So you have a completely free theory. So it's just you know, just a free theory as expected. So you kind of you send this guy to 0, and then you have just free theory. Okay. But now what we found as a kind of preliminary result is that when you compute the signal to noise ratio of some of the endpoint function, of the large endpoint function, you see that this signal to noise ratio is peak at some large n. Like for example here, this line, you take b tilde to be 10 to the minus 7, which is very small, and then this endpoint signal to noise ratio is peak at around 10 point function. So n is the number of legs, number of the external legs, okay. And then here for this value 10 to the minus 8, this peak around 15, and then here is peak around 20. So this kind of motivates one to look for in the observation, for example, to look for higher point function in the experiment. Maybe it's not too, maybe it's too too high in the for CMB, but then maybe for other experiment, like if you go to lower scale and so on, maybe one can look for higher point functions, and you see that the other low point function, like 2-point function or 3-point function or 4-point function, those are the subdominant compared to this large endpoint function. Okay, but okay, there always comes some caveat. Okay, there's been always some caveat, when considering about this kind of thing. So you might ask that when you reach this scale, lambda cutoff, or your new cutoff, it might be that your EFT might break down before this cutoff, okay? And then you have to you have to change completely your theory, and then you have to use the UV completion, whatever. And then this calculation, our calculation of the large endpoint function maybe doesn't apply, okay, because of this the breakdown of the EFT. Then we have to change our calculation and so on, but that we can leave to discussion. Okay, anyway, so I think my time is running, and then so let me just finish with my conclusions. So we have studied this detail of the distribution function of theta with this resonant features, and then we obtain we give the fully nonlinear action for scalar perturbation in the decoupling limit. So this action works as long as you can neglect the mixing with gravity. And also we numerically compute the non-perturbative wave function with these oscillating features. And the things for future directions are, maybe one can apply our method to others model of inflations, like when you have localized features and all that. Okay, as long as you can neglect gravity and you have small features compared to the zero potentials. And also what we are doing now is to consider large L limit and try to see how we can connect this large L limit to our large field limit, because these two limits are the limit where you go out of the perturbative regime. Okay, so you cannot use perturbation theory when you have very large external legs, and then that also one way to go beyond perturbation theory. And the last thing is to connect to PBH, but this is perhaps for next project, but not now. Yeah. Anyway, so if you have any questions, please, ask me. So, thanks a lot.
Thank you, Vicharit, for this nice talk. Are there any questions?
Can I ask?
Sure.
Sure.
So in your very beginning of the talk, so in the figure, it seems like the oscillations also decays as zeta gets larger. Is that true, or it always have this oscillation behavior?
Right. So from what we computed, the wave function, let me show you. Sorry, let me go. So suppose we use you take this saddle point approximation, and then you see that the amplitude is oscillating the wave function is oscillating in this theta bar, the amplitude of the time profiles. But if you fix p zeta, if you fix alpha here, this fix is that doesn't but okay, maybe there's some small dependence on theta here as you go to larger and larger theta bar. Okay, but here also this part is just the oscillation because there's an I here. Okay, so it's just you just change a bit of the phase of the oscillation, but I don't think it change any. Well, after you fix the alpha and p zeta here, I think it just some changes, but not much. Yeah, maybe there's some numerical factor here. Yeah.
But I thought according to your figures in the very early page, showing the oscillations explicitly.
You mean this kind of you
The very beginning of your talk.
right.
Yeah,
You,
around
this
yeah,
one.
this, yeah,
Well,
here.
you know, this figure is just for you to see schematically what happens to the wave function. So it's not the
Okay.
real calculations, you know.
Okay.
It's just to see how, or for you to expect when you expect the non-perturbative features to happen. Okay, so it should happen around here, but that doesn't mean that the amplitude should go down like this. And okay, it's just how to say to show you, you know, how the ideas how it's going to be. Yeah. But the actual calculation is in the last slide.
Okay, thank you.
Thanks.
Hey, there's a question in the chat. Naive question. How do you define the noise and signal to noise of endpoint function?
And the signal to noise is defined as you have the integration in over momenta, and then you have this endpoint function squared, okay, divided by the 2-point function to the n. So you have a endpoint function. So you have a bunch of, let me just write down. So you have a bunch of the integration in k, okay, depending on how, I to n, 1 to n. And then you have a endpoint function, theta until n, and then squared, and then divided by the 2-point function square to the n, and then this is a product, like a usual definition of signal to noise. Did I answer your question?
There's a thank you in the chat, so I guess yes.
Thanks a lot. Yeah.
Are there any other questions?
Thanks. I have one
Sure.
question. Oh, Zibang, you want to ask or?
You first. You go first.
So maybe a stupid question. I'm not really familiar with this. So the entire calculations here is based on the first order of B tilde, which is the amplitudes of the modulation.
That's right. Yeah.
So do you think like if you have sufficiently long e-folding, like the inflaton keeps rolling on that kind of modulating potential, would that tiny effects of B tilde somehow accumulate such that at some point you really have to go to like higher order B tilde?
Good question. Yes. Yes, we expect that, as you go to, long enough e-folding, so as you mentioned, then at some point one has to take into account these high order terms in B tilde. And at that point, we cannot use free solution approximation.
Right.
Yes. And then you have to solve the fully nonlinear classical solution for zeta or for pi. And then but you know, when B tilde is very large, it is very subtle because you might have your inflaton field might get stuck in some of the minima. And then, you know, you might have to change the pictures. Like maybe there's some decays, like vacuum decay, I mean. And then, you know, inflation stops there, and then we have to think what to do next.
Right. But my concern would be like, you know, from observations, we know that the e-foldings has to be sufficiently large. So if you really want to compare with observations, at some point, this kind of, I mean, you don't really have to consider the cases where the inflaton stops somewhere, but I mean, those higher order corrections at some point should still be taken into account if you want to really compare with observations. That's my concern.
Sure, I agree. If, like, for example, I think yes, like for example, if you really want to go to PBH, for example, then I think that would be important when for PBH. Yeah, then we have to do the full calculation, including like non-perturbative and also B tilde.
Sure.
Yeah, I agree.
Okay. Thanks. Thank you very much for the talk. Could you please explain one more time why the time in the Hubble is shift after you applying the Sternberg trick?
You mean in the EFC inflation, right?
Yes.
Yes. It's here, no?
The action.
Yes. Okay, let me start with this action, this EFT action. Okay.
Yes.
So the way we construct our EFT action is that so we identify our background field, which is inflaton background, as our time coordinate as t. Okay.
Yes.
So let me just write down here. So the way we can construct EFT inflation is that you take the background of a scalar field to be
Yes.
t, essentially. So
Okay.
after you choose this gauge, this is called unitary gauge. Okay. After you fix this gauge, it means that your symmetry of the action is 3D diffuse. Okay.
Yeah, I see.
Because you have already break time diffuse spontaneously. And that's
Yeah.
why in this action, you can have an explicit function in T appearing. Okay.
Yes.
And also other function like G00 upstairs, which is also invariant under 3D diff. Okay. So now after we have this action, this which is invariant under 3D diff, then you go to, because there's a trick called Zuckerberg trick that you can recover the full symmetry, because the full symmetry is the 4D diff. And in order to recover this 4D diff, you introduce a pi field, which is called Zuckerberg field. And then this pi field, then you have to do the shift from t to t plus pi. Okay. Well, I forgot to mention, in this case, in this unitary case, delta phi is 0. So you don't have a fluctuation in the scalar field. Okay. So you basically, in this case, you kind of put all the fluctuations of all the perturbations inside G mu nu, inside the metric. Okay. So in a sense, this G mu nu is absorb the scalar fluctuation. Okay. And now once you go to the pi gauge or you introduce the Zuckerberg field, now you recover the 4D diff. And now you see explicitly the scalar fluctuation and also the metric fluctuations. That's why when you see h of t or h dot of t, you replace everything with t plus pi.
Yes. So usually the unitary gauge is chosen directly by, as the time as the phi field itself. But
Yes.
now you choose the background value of the phi as the time.
Yes.
And you recover the
we choose the background because as you know, we want this time differ to be spontaneously broken. Yeah.
Yes.
That's the reason.
Yes. So,
but if you don't want to use this kind of EFT action, you can start from this.
So what makes me confused is that usually the unitary gauge is that you choose the phi itself equals to t, right? And now you can perturb the phi to be the background plus delta phi. Usually this term is equals to t.
Yes, you have this, no? You have phi is you decompose into background plus the perturbation, no? And then
phi
yes,
equals to t.
Yes, and then okay. So the transformation of delta phi is like this. Delta phi goes to delta phi plus phi bar dot t, and this t is a gauge parameter of the time diff. T go to t plus or minus t, whatever. I don't know, plus or minus anyway. Yeah. So now you can choose t just a way that delta phi 0 in the new frame. And this is a unitary gauge. Did I answer your question?
Okay. Okay.
Yeah, you can choose this big T to be the old delta phi divided by phi dot. And after you choose this, then the new delta phi in this case is 0. Something like that. But once you want to use when you want to recover or restore 4D diff, then you have to how to say, redo the thing, redo the
Yes,
theory. Yeah, you promote
yes,
this guy to be field, to be pi.
yes, it's not
Something
so,
exactly.
yeah, naively. I mean, as it looks. Okay, but thank you very much.
Yeah, thanks a lot. Thanks a lot.
Any other questions?
Yeah.
If not, I suggest we end the official part of the talk here.